Hello kids, today we will be covering Unit 8 for Grade 8 Science, which is rates of chemical reaction. So before we get into this, I will start off with a basic idea that what a chemical reaction is, right? So when we have, let's say, two chemicals, when we put them together in the lab, we saw that if we put mix two chemicals together, it does create a third chemical, which we call as a chemical reaction has proceeded, a new product, right? So we call these as reactants, right? And this is what we call as the product, right? So in a chemical reaction, so what is a chemical reaction, right? So let me define a chemical reaction, that two or more uh, chemicals form new uh, chemically, uh, or we can say new chemical, yeah, not chemical, new chemical products, right? And what do we mean by new chemical product? The term, this new chemical product, is really important, right? That means what we have as of A or B, this AB is not going to be the same, right? Let's say, as you can see just by the color, that if A and B were different colors, then AB is going to have an entirely different color. Secondly, we can also say that, as you can see, the bubbles are also coming out, right? Maybe this is volatile, right? It is vaporizing faster than this AB. So remember, the chemical composition of the product must be entirely different from the reactants. Now remember, let's say if you have salt and you put salt in water, that does not create a new product, right? That is just solution. So difference between chemical reactions and forming solutions is that over here an entirely new type of product is formed. So it has new properties, right, compared to AB. It is going to be entirely different from A and B. Let's say A and B were not acidic, but maybe AB turned out to be an acidic product, right? Let's say this was just, let's say, chemical A or chemical B, which were not acidic, but the resultant turned out to be an acidic product, and it can be very dangerous, and AB were not dangerous, right? So new properties or new chemical properties would be there, right? By properties, we are already always in chemistry referring to chemical properties, right? How the chemicals will behave. Now remember, in a chemical reaction, what we call as a law of conservation of mass. So this is law of uh, conservation of mass, right? That means if two things, let's say over here we have methane, which is like our common household stove gas, right? Which we use for cooking, right? The gas we use in our kitchen, right? It is reacting with oxygen when we ignite it. It gives carbon dioxide, right, as of a product, as well as water vapors, right? So eventually we will see that the weight of these products should be reactants should be equal to the products, right? This is what law of conservation of mass suggests, right? Now this we have discussed in unit 2 as well, right, as well as unit 5 previously in first term, right? How chemical reactions work, right? You can review that video again. Now, let me signify some of these factors when we are writing chemical equations, that reactants are the ones which are written on the left side of this arrowhead, right? And remember, this two, these represent coefficients, right? How many number of molecules are participating in the reaction. Now, this H2O, right, or this O2, or this H2, this represents the chemical formula, right? What type of chemical is reacting. And finally, one thing that over here in the diagram is not listed is this bracketed symbol, right? These are what we call as state symbols, right? State symbols. It represents what state of matter it is. Like over here we have S for solid, right? L for liquid, and G for gas. And we also have AQ, aqueous, if we're dealing with solutions, right? If we have solutions, right? In lab, we tried using several solutions like sulfuric acid with metals, in which metal was solid and the acid was liquid, and at times we used a diluted acid, which was the solution, right? Aqueous, we added some water to it, right? So anything that has water added to it is called an aqueous solution. Now remember, this is an additional topic compared to the book. It's the book considers that you know all of these, so they just move onward with the rate of reaction, right? So I'm just giving you a background information. Now we have types of reaction. We have several types of reactions, right? In which at times we have two products, A and B, joined together to form a new product. This is what we call as addition reaction, right? In which two things add up to form a new product, right? Then at times we have a product which is formed of two things and we heat it up together, right? We usually heat this. They separate, right? This is what we call as decomposition, right? That we decompose one chemical into two separate chemicals, right? This is called decomposition, right? Usually we call it thermal decomposition because we usually heat things to break this down. Example is calcium carbonate, right? We heat calcium carbonate to get calcium oxide plus carbon dioxide, right? This is a decomposition reaction, and this could be H2 plus O2 giving you water, right? H2O. This is addition reaction. Compared to this, we also have displacement reaction, right? We have covered displacement reaction in detail, right? Where we saw that more reactive metal is going to displace a less reactive metal, right? So this is what we call as displacement reaction. Then we have double displacement reaction, right? In which both the components uh, replace positions. For example, over here D has replaced B, right? And we can also say that this B has replaced D. So we have double displacement reaction right over here, in which two things are changing places compared to this first one, which is a simple displacement reaction. It is also a type of displacement reaction, and except it has twice the particles moving around rather than just one. Right now, this was a bit about chemical reactions. It's a little bit of a prenup for the rate of reaction. Now, let's say, sorry, let's say we're talking about a reaction in which water, let's say, is formed. H2 plus O2 gives you H2O. So when the reaction started, right, only the reactants are there, right? This is concentration. So you can see that the reactants are at the top position and the products are at zero, right? So max, and products are at zero. Why the product is zero? Because there is no reaction started. The reaction has not started yet. So definitely they're only going to be reactants, right? And as soon as the reaction starts, you will see that the reactants will start to reduce since they are reacting and forming new product, right? So you will see that the concentration of the product will increase while the concentration of the reactant is going down up to a point where it attains a straight line, right? This shows completion of reaction, right? That the reaction has completed. Some of the reactants may not react due to some external factors, right? Let's say if it were a reversible reaction, then obviously some of the product will be some of the reactant will be remaining, right? As you saw, let's say in the reaction, we if you remember in the lab, we put magnesium ribbon and acid, right? You saw that after a while that the magnesium ribbon was gone, it was consumed, right? Gas came out, right? The bubbles came out, and the acid was still there. So you can say that the reactant was, some of the reactant was left over, right, after completion of reaction. So how fast the reaction is going to go forward and backward is what we call as rate of reaction, right? So this curve changes with different factors that change over time, right? So this is one assembly that we use how to measure rates of reaction, right? So let's say this is I will label this diagram. This is the measuring cylinder, and please don't mind my writing, as you can hear the words, and this is what we call as water bath, right, or water turf. You can check the spellings. My writing is a bit joining, so you can check the spellings on the internet as well. This is what we call as delivery tube, right? It delivers gas from the reactant zone into this gas chamber or gas collection area, right? This is conical flask. We have used this, right? And this thing over here is called thistle funnel, right? And this thistle funnel is a specific one. It also has a valve, right? This is what we call as valve. Usually we don't have thistle funnels with a lab, and this cork, or we call it cork, or usually bung, right? If it's made out of rubber, we call it bung. If it's made out of wood, we call it, cork, right? So it's the same thing. It allows the gas to go, from just one point into the delivery tube, and then it's collected over here, right? How much gas is collected and how much time, right, gives us the rate of reaction, right? So how do we measure the rate of reaction, right? We say that the gas, sorry, right? We call this as gas collected over time, right? And why what additional apparatus will need is a stopwatch, right? Because we need to know how fast the gas was collected, and once the bubbles stop coming, that's when we say that the reaction has stopped, right? So when do we start, right? Start would be start of bubbles, when the bubbles appear, right? Start of bubbling, when the bubbles will start to appear, and end of the reaction would be when bubbles stop, right? When there are no more bubbles coming up, right? Bubbles stop. That's when we stop. So the time taken for this is called the rate of reaction, right? How much time did it take to do this reaction, right? Now it depends on several factors, right? We will cover those factors. We have covered this in classroom as well, right? It was a very simple topic, so we did this in just 2 days, right? In classroom, right? Because of a very simple idea. If you remember, I gave you the collision theory, right? That eventually is the collision of the particles that result in new products, right? So if we in now there are three factors that we're studying. There are more as well, but at your level we're only just covering three factors, right? Number one is the temperature, right? So if you increase the temperature, we do know that increase of temperature results in increased movement, right? Increase of temperature results in more movement, and obviously when things will move faster, then they will have more collisions, right? So remember the collision theory. I told you that for O levels, I'm bridging this topic for O levels. In O levels we use collision theory. In your book, collision theory is not referred, but I just told you that everything that results in more collisions of the particles will result in more rate of reaction, right? So increasing the temperature will definitely increase the movement of collisions, movement of particles. Having more collisions means more product is now forming, faster product is forming. So if you look at this temperature curve, in this temperature curve we can sorry this time rate of reaction curve, we can say that both of them, when straight line appears, that reaction has completed. But you can see that the pink one became straight when there was more temperature, right? So with a higher temperature, we saw that the reaction completed faster. Whenever there's a straight line, it shows completion of reaction or the reaction has stopped, compared to lower temperature, in which you can see that the green line is still curved. It is getting closer to completion of reaction, but very late compared to this one, right? So this is a very simple representation of how the rate of reaction if is affected by temperature. The more the temperature, the faster the reaction is going to be. The lower the temperature, the slower the reaction is going to be, right? Now in contrast to this, we have effects of concentration, right? So I took my time and drawing this for you people. I doodled around, I was just when I was making this revision lesson for you people, right? So having more concentration means more particles, right? So if you look at this, if we have fewer particles over here, right? With fewer particles, there are fewer collisions possible, and definitely, if I increase the number of particles, right, add more concentration of the liquid or the reactants, you will see more collisions, right? Now, over here, we're not having 100% collisions, reason being we're not increasing the temperature, right? We're only increasing the number of particles. That means more possible collisions, right? So we say that more particles means more possible collisions. It not necessarily mean that all of them will start reacting immediately, but uh, it does mean that more particles, more collisions, right? That this is how it works. So in this case, we will again see that this is the mass of the product and the time start, right? As you can see, more concentration completed faster, while slower concentration completed later on, right? So it's the same effect. Remember, the diagrams appear to be the same. You just need to be able to identify that the high concentration or higher pressure will result in more collisions, while low concentration or low pressure will result in uh, less collisions, right? Hence, the rate of the reaction is going to be slower, right? Uh, Now moving forward, right, I'm again going faster through this because it's a very simple concept. You just need to be able to, identify these diagrams. You're not supposed to, go into detail, right, because it's a very complicated concept for O levels. So at your level, we're just going through a basic of this diagram, and we usually get to plot given data, right? So charting this is important. Other than that, there's nothing very complicated about this. Just go through the workbook questions and refer to this basic idea, these diagrams, if you want, if you have any confusion, right? Finally, we discussed the effect of surface area. Definitely, if you have things, again, we talk about the collision. Remember, I've chosen these diagrams very specifically to emphasize on collision theory, that let's say if you have a bigger block, like we call it as lump versus powder, right? If you have powder of a substance and you have a lump or a bigger stone of that substance, then definitely powder will react faster because it will allow more faces or more surface area for collisions to occur, right? Compared to a lump, which will only allow a possible less surface area for the collisions to occur, right? And in the same way, if we look at the difference of these two, right, in which we have powder versus lump, we will see that the powder will end up faster, the reaction will complete faster compared to lump, which is completing again very late, right? So the time for reaction is going to be faster for this and slower for this, right? It will take less time to complete when you're using powder as a chemical, and if you use large stones or lumps, we will have a slower rate of reaction, right? Now I hope this is a bit of summarization of the things we have discussed in the class. As I said in the class as well, that this is a very small topic, except the activities are there. The activities appear to make this unit very long. On the contrary, even in the O levels, it is just a very small little topic, except they emphasize more on the collision theory and more on the type of chemical reactions that are taking place at your level. Since the type of reactions are not included, the things we have discussed over here, right, since they are not included in your level, so just understanding the effects and how the rate of reaction is affected by these factors, that is all required at your level. So it's not much of a bigger topic to cover, so it's a very small topic, so hence it's a very small lesson that I've made for you people in terms of revision, right? Hopefully this is adequate enough for you people to go through the workbook questions. If you still get any queries, any issues while solving any of the workbook questions, just send me a picture of that question, and I'll definitely be giving you advices on how to approach that question. And obviously I'm not going to give you any answers to those questions because you have to solve the workbook on your own. If you get any trouble, just give me a text. I'll help you cover those questions, right? Thank you.